Hello and welcome back to High Level System Design series. Today we will discuss about how we can design a rate limiter. In this session, we will understand why do we need rate limiter. We will understand how can we gather the necessary requirements for this high level design. We will also discuss about back of the envelope estimation. We will design the system and we will identify the issues. We will solve those issues by refining our design. So at the end of the session, we will have a concrete high level design of rate limiter which can handle millions or billions of users. What is rate limiter? Rate limiter is a system which limits the request to a server. Using rate limiter, we can also protect our system from denial of service attack. In this attack, basically the attacker will send a huge number of requests to the system so that your system will not be able to handle the load and it will go down or it will crash. That is known as denial of service attack. We can also enable our application as multi-tiered application where we can have a limit for community or free users, but there will be no limit for premium users. Such kind of limitations or tiering can be done with the help of rate limiter. Hence, rate limiter is a very crucial system for the services or applications we expose it to the internet. If you are asked to design a rate limiter, you first have to gather the requirement because different requirements will influence your system design, such as is it a SaaS product we are designing? Should we rate limit based on the user ID or based on the IP? Who will specify the rate limiting rules? What is the DAU of the system we are expecting? What to do with the requests we will be dropping or throttling? These requirements are very important for our system design because if it is a SaaS product, a number of applications will use this rate limiter as a managed service. That means the same rate limiter will be used by a number of applications. In such cases, obviously the design will be different. Let's assume in our session, we are not developing any SaaS product, but we want to design this rate limiter for our existing application. We also need to understand how can we limit the incoming request. Is it based on the user ID or IP? Both will work, but based on the use case, we will choose either user ID or IP. For example, if your system or application does not have any user registration process, in such cases, you will not have any user ID. Rather, in that case, you have to rely on IP address. Now, who will specify the limiting rules? Is it the same organization? Or in other words, how can we get the rate limiting rules is also an important aspect. In order to understand the scale of the system, we also have to understand what is the daily active users of the system we are expecting. And finally, if we are dropping or throttling any incoming request, we should know what to do with that request. We can simply drop the request without even informing the client. We can log the request for our future analysis. We can inform our client that he or she has reached the rate limiting threshold. So answer to these questions are critical for your rate limiter system design. For our session, let's say it is not a SaaS product. We will rate limit based on user ID. Let's assume we have the rules already. We are expecting 1 billion users a day and we will be logging the dropped requests for our future analytics. Once we have enough knowledge about the system we are going to design, we will quickly understand the scale of the system by performing back of the envelope estimation. As we know, the expected load of the system is 1 billion DAU. So average QPS or queries per second will be, if you do not understand why we are dividing 10 to the power 5 here, you can check out my back of the envelope estimation video where we have seen if we know the DAU or daily active user, how quickly and easily we can convert it to the queries per second or transactions per second. Here we are converting a day into seconds, and instead of 86,400 seconds, we are rounding it off to 10 to the power 5. But for details, obviously you can watch my previous video where we have discussed about back of the envelope estimation. 1 billion means 10 to the power 9, hence 10 to the power 4 requests per second will be the queries per second or QPS. In order to estimate the space or storage requirement, there will be two types of data. One is rate limiting rules, another is keep track of the number of requests for every users. Rate limiting rules will be simple JSON files which will be common across all the users most of the cases. However, there could be some specific rules for set of users. As it is a JSON file, the size of rate limiting rules will not be very big. Let's assume it as 1 GB, and rate limiting rules will modify infrequently, and it is not very much dependent or directly dependent on the number of users we have in the application. Whereas count of requests will be there for each active users. Hence, if we have 1 billion DAU and assuming 10 bytes to maintain the count of the requests of a specific user, it will be of 10 GB. During the session, we will use these values to influence our design. Let's understand how. With this requirement gathering and back of the envelope estimation, we are ready to start our high level design of rate limiter. For a rate limiter system, we will have users who will send requests to our application server. However, rate limiter resides between user and application server. So all the users' request will go via rate limiter. Rate limiter application will have the rate limiting rules which are there in the database assume. Based on these rules and request count of this user, rate limiter application will decide if the request will go to the application server or not. If the number of requests for this particular user is more than the threshold value based on the rate limiting rules, it will drop the request. It will not forward the request to the application server. In such cases, based on the requirement, as we know that we have to log the dropped or throttled request, we will write log here. So to summarize, once user wants to connect to our application server, we will have the rate limiter system in between. What is the purpose of this rate limiter? Based on the user ID, it will check how many requests the user has triggered so far, and based on the rate limiting rules, if the user is eligible to connect to the application server or not. Based on this decision, rate limiter will either forward the request to the application server or it will drop the request and log it for our future analytics. If I speak about flow, this will be 1, this will be 2, because we need the rules in order to understand if the request will be a valid request and it will be forwarded to the application server or not. This will be the third step where we will check number of past requests for this user, and based on the condition, it will either go to the application server or it will be dropped and logged into our application log. Hope so far you have understood the high level design of this rate limiter application. Now the question is where to store this request counts. We can keep it in two different places. One is in DB or in primary memory of server. From our back of the envelope estimation, we have seen that we have to process nearly 10 to the power 4 requests per second or 10k requests per second, and DB takes 10 to 100 milliseconds to process a request. That means in 1 second we have to process 10 to the power 4 requests. Per request we have 100 microsecond. Now if we keep it in DB, for each read it takes 10 millisecond. So obviously DB is not the solution for storing request count per user. We have to store it in the primary memory of the server. See how back of the envelope estimation is helping us to take design decisions. So let's draw the refined design now. We will have user who will send request to the rate limiter. Rate limiter will check the rules where we will have the threshold value for number of requests per user. We will keep the request count not in database but in primary memory of the server. We can do that using cache, where basically we will have user ID and count, which is nothing but the request count. And based on the decision, it will forward the request to app server or it will log the requests which are getting dropped. Now the similar problem will arise while fetching the rules as well. For request count also, we have seen that we need to serve a particular request in 100 microsecond. However, database read is taking at least 10 milliseconds. Hence, we will not be able to achieve the 100 microsecond requirement. The same logic also applies to the rules as well. If we fetch the rules for every request, our request processing time will not be within 100 microseconds. We need cache here as well. If you do not know what is cache and how to use it, you can watch my previous video on system design where we have explained the need of cache in details. So in our enhanced design, we have added cache in both the places. In our previous video, we have discussed what is the use of cache and how it is enhancing the performance of the overall system. Here, we have seen from our back of the envelope estimation that our system has to process a single request within 100 microseconds. And if we want to read the database per request, we will not be able to achieve the requirement of 100 microseconds. Hence, we have introduced cache in both the places. This cache will actually keep the counts of requests per user, and this cache will keep the rate limiting rules. I hope so far you are with me. Now let's see what are the other issues we have in this refined system design of rate limiter system. Now in our design, single rate limiter server is an issue. It is single point of failure and it will not be able to handle high or bursty load of our system. Hence, we need to have multiple rate limiter servers. Let's assume we have 3 rate limiter servers, rate limiter 1, 2 and 3. If we have 3 different servers, we have to have a load balancer which will distribute the load among these rate limiter servers. Hence, our user will not directly communicate with the rate limiter server, rather it will send the request to our load balancer. Based on the load of each and every rate limiter servers, load balancer will decide a specific server to process this request. Let's assume load balancer sent this request A to rate limiter server 2, which will either forward this to the app server or it will drop the request based on the rules and the request count of the user and write a log for this request. Hope you have realized why a single rate limiter server will not be sufficient for our system design because of 2 reasons. One is it is a single point of failure. If server goes down, then all the requests will not be processed and it will go to the application and our application will be unreachable. Second, it will not be able to handle the high and bursty load for our app server. Hence, we have added 2 more rate limiter servers, and as we have 3 rate limiter servers now, obviously we should have a load balancer in front. If you don't know why load balancer is needed in this case, please watch my previous videos, and based on the rules and the count of the requests, either the request A will finally reach to the app server or it will be dropped and a log entry will be added in our application log. In this way, we are eliminating the single rate limiter server issue. But this lead to another issue. Assume we have request count for user A in rate limiter 1 and the subsequent request from user 1 is going to rate limiter 2. For rate limiter 2, the request count is 0. But for rate limiter 1, for the same user, request count is 3, for example, because each and every rate limiter is keeping this cache where we are storing user ID and count. So obviously, as we have introduced load balancer and 3 different servers, for the same user, there will be different counter value in different servers. Hope you have realized the problem. Earlier there were single server and that particular server was keeping the cache or user ID and count. There were no issues. However, now we have multiple servers and each servers are keeping its own count. Hence, for a single user, let's say user 1 will have the count value 2, for example, in server 1, count value 1 in server 2 and count value 5 in server 3. It can happen. In that case, our rate limiting rules will not be applied, and even though number of requests from a specific user has reached to the threshold value in one server will not affect the counter value in other servers for the same user. How can we solve this problem? Option 1 is sticky session, through which we will be ensuring that a particular user will be served by a specific server. How can we implement this? Let's assume user ID is a numeric value. Very naive idea is we can perform modulus operation by server count. Hence, a request from particular user will always redirect to a single server and we will keep the counter value for that user into that server. Everything will go fine unless the server is crashing. In real world, crashing the server or a particular server is going down is a very common behavior. Hence, sticky session will not be a long-term solution. Option 2 will be the common storage to keep the counter. In that case, we can keep a Redis server, which is nothing but a key value store, where we will keep the counters. Key will be the user ID and value will be the current count, and we will make sure that all the rate limiter servers are relying on the value stored within this Redis server. In that way, even if one server is going down, we will not lose the counter. We can always add the new server here, and the new server can refer to the Redis server in order to get the count of a specific user. We do not need sticky session in this setup. Load balancer can send any request to any server. Redis is a distributed cache. That means Redis has a number of servers to keep the key values. Apart from this, Redis also replicate the data in order to enhance the durability of the data. Hence, even if one Redis server is going down, we will not lose the count of a specific user. In that way, we are foolproof with this design. There can be one more issue with the Redis called race condition. Let's understand what it is. Assume for a specific user called A has current count of 4. In this situation, if user A sends another 2 requests to the load balancer and one can go to rate limiter 1, another can go to rate limiter 2. Both will read the value 4 as the count if they are processing the request concurrently and increase the value by 1, and both will try to write the value 5 into the Redis server as count. However, this is wrong because after this situation, user A has sent 2 more requests. Hence, the value should have been 6 instead of 5. Why it is 5 instead of 6? Because both the servers have read the value 4 as counter value at the same time. This situation is known as race condition. The solution for this Race condition is sorted set data structure available in Redis. If you want more information on sorted set, you can search in the internet. But if we keep the counts within sorted set, race condition will not arise. Now let's understand how rate limiter algorithm works. Let's discuss basic rate limiter algorithms. We have 4 basic rate limiters algorithm what we have to remember. Token bucket, leaky bucket, fixed window, sliding window log. These are the 4 important and basic rate limiter algorithm what we should know. Apart from these 4, there are a number of custom algorithms what you can build on top of these 4 basic algorithms. Let's understand each one of them in detail. In token bucket algorithm, we will have an imaginary bucket where we will keep the tokens in a fixed rate. So for example, our tokens will come per second in this bucket for a specific user. As and when user's request comes, it will check if we have tokens present in the bucket or not. If token is present in the bucket, one token will be deleted and then the request will be transferred to the server. If there is no tokens present in the bucket, user's request will be dropped. What is the pros here? It can handle bursty traffic, because if user is not requesting for quite some time, we will have the imaginary bucket full of tokens. In the very next moment, if user is sending a large number of requests, it will be processed because we will have lot of tokens present in the imaginary bucket. So it can handle bursty traffic. This is a very easy to implement algorithm. Let's discuss about the issues we face in token bucket. There are 2 different parameters to tune. One is bucket size and second is the rate at which tokens will come into the bucket. And as there are 2 different parameters to tune, it takes a lot of time to tune the bucket size and the arrival rate of the tokens. So token bucket is an algorithm which creates an imaginary bucket for each user, and there will be a constant flow of tokens into that bucket. Bucket will have a specific bucket size as well. Whenever there is a new user's request will come, it will check in the imaginary bucket if we have the token present or not. If present, then we will remove that token and we will pass that request to the server. If there is no token present in the bucket, it will drop the request. Let's understand how leaky bucket is different from token bucket. Unlike token bucket, leaky bucket uses queue, and this queue has a fixed size. As and when we get user's request, we check if the queue is full or not. If it is not full, it will be added at the end of the queue, so that request will be processed sequentially one after another by the server. If the queue is full, the request will be dropped. So all the requests are processed at a fixed rate, and this algorithm is memory efficient too, easy to implement. One of the major cons of this algorithm is it will not be able to handle bursty traffic. Hope you have realized the difference between token bucket and leaky bucket. If you have some use case where you have to handle bursty traffic, then token bucket is the way to go. On the other hand, if you want to handle the requests in a fixed rate, leaky bucket is the better option. Let's check how other 2 algorithms work. In fixed window, we define fixed size window of say 1 minute. In 1 minute, we decide how many requests we will approve. Let's assume we will approve 3 requests per minute. So in this case, in the very first minute, all 3 requests will be approved, whereas in this 1 minute window, we received 5 different requests from the same user. But as per the rate limiting rule, we will only approve 3 requests. The other 2 requests will be dropped. This is also a very simple algorithm. However, it has a major con. Let's understand it in detail. Let's assume this is the 1 minute window. This is next 1 minute window. Now, if the requests are coming near to this edge of the minute, then these 3 requests will be approved. Why? Because we can approve 3 requests per minute. Similarly, if another 3 requests are coming exactly at the start of the next window, it will be approved, because next minute we can approve 3 requests. However, if we take this 1 minute window, which is starting from 30 seconds of the first minute and ending at 30 seconds of the next minute, here we are approving 6 requests instead of 3. Hence, bursty traffic at the edge will not follow the rate limiting rules. And that is the reason sliding window came into picture. In sliding window, we are keeping logs. The new logs will be appended in the log files along with the timestamp. As and when a new request coming in our system, we will first remove all the entries of this log which are outdated, which are of outdated timestamp. And then we will check how many requests we have in a specific timestamp interval. If 2 requests are allowed, for example, then the first request will be processed. The second request will also be processed. Why? Because second request assume coming after 30 seconds. We check what is the previous timestamp which are there in the log. We saw the previous timestamp was at 01. So even the second request will be processed because we have 2 requests so far. And as per rate limiting rule, assume we can process 2 requests per minute. When the next request is coming at 50 seconds, we see already we have 2 timestamps which are not outdated. One is at 1 second, another is at 30 seconds. So the request which is coming at 50 seconds will be dropped because our rule is to process 2 requests per minute. Now let's assume the new request is coming at 1 minute 40 seconds. Then it checks the previous timestamps logged in this log file. One was at 0001 which will be outdated now. One at 0030 which is also outdated. One at 0050 which is not outdated. One at 0140 which will be processed now, because the outdated entries are deleted first and then we check how many entries are there in the log file. If it is 2, then the new request will be dropped. If it is less than 2, the new request will be processed. Pros here is in sliding window log, we handle the bursty traffic at the edge of the window. However, the memory consumption for sliding window log will be more than previous algorithms. It is not a memory efficient algorithm because we are also keeping the timestamp here. Now let's discuss additional points related to rate limiters. There is one HTTP status code 429, also known as too many requests. In case you want to return a message to the user while dropping the request, you can send HTTP status code 429 so that user can understand that the request got dropped because of rate limiter rules. Along with status code 429, we can also set few flags in the header of the response. We can inform the user by setting a HTTP header flag in the response saying that rate limit retry after. As soon as client receives that response, they will understand that the next request has to be sent after some time. So in order to inform the user, we can send a HTTP status code 429 and set the header with rate limit retry after flag. Apart from this, it is important to monitor if the rate limiting rules are effective enough. If they are not, you have to modify the rate limiting rules accordingly. Hence, monitoring is important. In order to avoid single point of failure, we can do multi-data center replication as well. If you are not aware about multi-data center replication, please watch my previous video in this series. Let's summarize what we have learned so far in this session. In this session, our intent was to design a resilient rate limiter. We realized what is rate limiter, what is the use of it, and then we went through requirement gathering phase where we gathered more information about the system we are trying to design. Then we perform back of the estimation in order to understand the load of the system. We calculated QPS, query per second, and the storage requirement for the system. We came up with the initial high level design of rate limiter. Rate limiter system needs a storage to store request count for each users. We had two options. One, store it in the DB. Second, store it in the primary memory of the server. Based on the back of the envelope estimation, we realized we need to serve a single request within 100 microseconds. If we choose DB to store the request count, a single read to the DB takes at least 10 milliseconds. Hence, we will not be able to store the counts in DB. The choice is to keep it in primary memory. We used cache to keep user ID as key and count as value. Similarly, the rate limiting rules were in database. For each and every request, we cannot consult the database for rate limiting rules. We need cache for it. After modifying our initial design by adding cache, will enhance the performance, will reduce the overall service time of a specific user's request. Then we realized a single rate limiter server is prone to single point of failure, and it will also not be able to handle high or bursty load. The solution is to have multiple rate limiter servers. Once we introduce multiple rate limiter servers, we needed a load balancer so that the request will come to the load balancer and load balancer will decide and forward the request to one among multiple rate limiter servers. We faced another problem because we were keeping the count values in the primary memory of the server. Then we either have to ensure that a specific user's request is always served by a specific server, also known as sticky session. Otherwise, there will be different counts for the same user in different servers. Hence, our rate limiting rules will not be applied correctly. However, sticky session has a number of problems. The server can go down, then we will lose the count. A particular server will have tremendous amount of load where other servers might have very less load because of sticky session. To solve such situation, to solve that issue, we went with option 2, where we will keep the counters in a common storage and we will ensure that all the servers are consulting the storage for counts. We had chosen Redis key value DB for this, where we will keep user ID as key and count as value. We also discussed about race condition while modifying the value of a specific user ID and realized that Redis has a very good data structure to handle this problem called sorted set data structure. With our final design, our system can handle a large number of load because we have multiple servers now and we can scale it up as and when needed because these servers are stateless. We are not going ahead with sticky session. So as the servers are stateless, we can always perform scale up and scale down without any issue. Based on our requirement, if we are dropping any request, we will be writing the log in our application log for future analytics. Finally, we discussed a number of rate limiter algorithms. Token bucket, leaky bucket, fixed window and sliding window are 4 fundamental algorithms used for rate limiter. Apart from this, many organizations write their own design, their own rate limiter algorithm based on the use case. But these 4 are the basic rate limiter algorithms what you have to know. Finally, as a part of additional points, we discussed about the HTTP status code in order to respond to a user where we are dropping its request. HTTP status code 429, also known as too many requests, will be the status code for our response to the user. Along with 429 status code, we can also add a flag into the HTTP header called rate limit retry after, so that user will understand that his or her request got dropped because of rate limiter, and the subsequent request from the user will be after some time. Monitoring the rate limiting rules is also an important part of the rate limiter design. If we feel that the rate limiting rules are not effective enough, we have to modify the rate limiting rules as and when needed. Finally, multi-data center replication is another aspect for rate limiter design, because if we keep all the servers in a single data center and that data center goes down because of any reason, our whole application will go down. Hence, multi-data center replication is needed to keep our application available. Hope you have enjoyed this session. If you have learned anything new in this video, do not forget to like this video. Thanks a lot.